So we'll continue today in our effort to lay the foundation for understanding elliptic functions and elliptic integrals. And we just did the integration of rational functions, which was a review of, I wouldn't say totally elementary calculus. It's considered elementary calculus, however. The level of detail of the last lecture, which was the integration of rational functions, that's very course dependent. It depends on how much energy you put into the sort of foundations of calculus in your calculus class. If you took an engineering calculus class, you probably didn't go through it in nearly as much detail. But now we're going to do the integration of rational functions involving this square root term, this radical term, where the independent variable is z, and you have cz squared plus bz plus a. Now I know that we almost always do quadratics ax squared, well, az squared plus bz plus c. We go the other way around. But for some reason, Gradstein and Risdick, the very famous book about integrals and sums and series of integrals, actually it's titled Tables of Integral Series and Products by Gradstein and Risdick. It's just a legendary reference. It prefers to use this nomenclature. The quadratic constant is c, the linear constant is b, and the constant itself is a. And we're going to call that whole thing S, right? So S is actually defined by that term. And that's because this term shows up so much in our work that we just give it a little symbol. So we're going to integrate rational functions of S, but the independent variable is Z. So that's important to remember. But we're going to integrate rational functions of S. So what is a rational function of S to begin with? Well, a rational function of S is defined exactly the way we did rational functions of Z, except now, so here's the S squared sk. It's the ratio of two polynomial-looking things, but each of these coefficients have to be understood as a rational function of Z. So that whole material we did before on rational functions, this is a rational function of Z. So A0 is a rational function of Z, A1 is a rational function of Z, A2 is a rational function of Z, likewise B0 and all of these guys. Let me get rid of all those because they're a mess. So in some sense, things are becoming a little more abstract in their appearance here because now these letters no longer represent just constants of a polynomial. They're now rational functions of Z. So we're going to speak about this in pretty good generality, though, because we can simplify this quite a bit. We also must remember, too, that this can also be, so the way we want to look at, so we can simplify this quite a bit. So what do we do to simplify it? Well, we first understand what is S squared. Well, S squared is CZ squared plus BZ plus A, which we will sometimes write as A Z minus the first root times Z minus the second root. That will be a typical standard way to do it. However, this could be complex roots. If they're complex roots, we'll probably leave it in this form, right? So if the roots are real, you can always go to that form. If the roots are complex, you can go to that form. If you're willing to consider Z as just a complex variable, then you can always use this form. You can always use this form if that's your interest. This is all legit for complex variables. Everything we're doing here is legit for complex variables, but we're going to kind of lean into the way you want to look at it for real variables. So now, with this in place, let's take a look at, say, this term here, or a random term in the denominator. We'll call it b sub I, which I'll go ahead and point out as a rational function of Z. So I'll put the Z in there, s to the L power. Well, let's imagine that, not L, I, right? It's going to be I, S, I. That actually looks like a summation over all the indices I, so you might look at this and think that's the whole polynomial, right? Because we've got an upper index and a lower index and we're summing. But for the purposes of when we study mathematics in this context, that's not what that means. We're not doing the summation. We're now in a form of the mathematics that I is just a given index. And we've just sort of arbitrarily gotten lower ones and upper ones here. That was our sort of our choice. Actually, yeah, so we're not doing the summation convention because I is actually an exponent, right? I guess that's the way to think of that. I is literally an exponent. So S7 is not some superscript. It is literally S times S times S times S. So that's the big hint that this is not an Einstein sum. That's probably the better way of thinking of it. But let's take the example where I equals 2, say I equals 2. So we would have some polynomial identified by B sub 2, and that is a subscript, by the way. Well, not that there's an alternative. And then you would have S squared. But of course, S squared is just, so this is B sub 2 Z multiplied by CZ squared plus BZ plus A, right? And that is just another polynomial, maybe I'll call it P2 of Z. It's just another rational function, not a polynomial, but a rational function. If this is a rational function and you multiply it by this small polynomial, you get another rational function. And that will always be true for any even power of I, right? If I put in 2n up here, I would basically get this raised to the nth power, which is still just another polynomial. So every even term in the numerator and the denominator really goes away and just becomes a polynomial. But what happens for the odd terms? Say I did B2, well, let's say B, so I guess this would end up being B2n, S2n, right, to make everything fit the notation we're doing. So let's do B2n plus 1, S to the 2n plus 1. And in that case, you'll get a polynomial multiplied by S, right? You'll get a polynomial in Z multiplied by S because this part is just another polynomial in Z. And then you have 1 left over, which is this. So that's always going to be P2 square root CZ squared plus, this is P2 of Z, BZ plus A. So that realization actually brings this guy into a much tighter structure than would initially appear. In particular, I can rewrite it. And shockingly, it reduces to this little thing. It reduces to some rational function living in the left-hand side of the numerator plus a rational function multiplied by S. All that's in the numerator. And then you have another rational function plus a rational function multiplied by S again. And so that is what the rational function, any rational function of Z and S is going to end up in that form. So now take this object and multiply the top and bottom by B0 prime plus B1 S, B0 prime plus B1 prime S. So we multiply it by 1 basically. And what do you get? Well, you get something that looks like this. The simple expansion of this will give you a constant term, 2 terms that are linear in S, and 1 term that's linear in S squared. But of course, that S squared is just another polynomial, and that S squared is this little quadratic, right? This little quadratic piece here. And that S is the radical, that S is the radical. That's going to be a rational function, and these coefficients are rational functions. In the downstairs, you get, it's all a rational function, right? Because S squared is a rational function, and these two are rational functions. So that's totally, so the downstairs is completely rationalized. This is very similar to eliminating complex numbers in the denominator. That's incorrect, right? It is similar to eliminating complex numbers. So I need to do sort of the conjugate, right? You need to multiply by the conjugate of the denominator, B1 prime S. So I changed this from a plus, which I had accidentally written to a minus. That's the origin of these minus signs, or these minus signs here. The idea of the complex conjugation comes from the fact that s squared is a rational function. So this is going to be rational too, just like I squared would be -1 or something. But the point of the plus here and the minus here is to get this to be the difference of squares, which of course I've also screwed up, right? There's got to be squares there as well. But let me double check this whole thing. Yeah, okay. So now I finally got it. So, but the point of all this is that if you go up to the top, you say that's rational. That's a rational function of z only, right? Because the s squared goes away. This is a rational function of z only, and these two can be combined to be a rational function of z multiplied by s. And the denominator is a rational function of z only. So if we called this, I'll give it the letter E, right? And we split the top into a rational function of z, which I'll call, say, c of z, plus another rational function of z, which I'll call d of z times s, this whole thing is going to equal c over e plus d over e times s. Not times s. Yes, times s. Therefore, our integration of a rational function of z and s, and this, of course, the integration is respect to dz. Z is the independent variable. It's easy to get lost in that, right? And to get like, oh, s's and z's, and you got to think, okay, s's is substituting for this thing, and it's very easy to, if you read books on the subject, especially the older ones, you get layers and layers of substitutions and abstractions. But, you know, it's how you learn to concentrate, I guess. This ends up being the integral of, well, what is this? That is a rational function of x. I'll call it p of x. Or I say x. I meant that is a rational function of z. I'll call this p of z. And we'll call that, okay, so what we're going to do there is we're going to say that this term equals ds squared over s, over es, and the numerator, because you got an s squared, is a rational function again, and then divided it by e, it's still a rational function, so that whole thing is going to be q of z over s, right? Everything's always these rational functions. So that's going to be the integral of p, this rational function of z, dz, plus the integral of a different rational function of z over z. So if any rational function of z and s can always be written in this form. That is, rational function, the integral of a rational function, which we know how to do from the last lecture, and then, shoot, why did I put a z there? It's an s, right? See how confusing it can get? And plus this piece here, which is the critical part, right? This is the part. It's an integral of a rational function of z divided by s. So here's the beast written out, where I've substituted everything back. QZ is now this rational function. So any rational function of z is has a numerator and a denominator, and that's going to be, say, a polynomial number 1 in z divided by a polynomial number 2 in z. And you do your long division thing like we did in the last lecture, and you get a polynomial in z plus, let's call it q sub 1 of z, another polynomial in z. I like to put lines in my z's, but these z's are a little bit too bulky for me to keep control over. So there'll be a polynomial in z, and then let's see. This has to have this part is the pure polynomial part, right? That results from the long division of this thing. So this guy's got to be another rational function. I'll call it q1 over q. I'll say d for denominator. All you have to know is that there's a polynomial in numerator and a polynomial in the denominator. And I'll distinguish them by calling this one Q1 and Q denominator. And therefore, this integral here, right, you substitute this for QZ, and you have to get that to equal the integral of a polynomial in Z over S dz plus the integral of a polynomial in Z over another polynomial in Z divided by S dz. Like that. The first integral is relatively simple to break down. And it's very obviously this is a polynomial now in Z. I guess Q is the rational ones. The capital ones are rational, and then P's are polynomials, little ones are polynomials. You have to move it through fast enough so that you don't forget what your notation is, right? But this is a polynomial, so these now are constants. So I've kind of made them lowercase just to remind myself that they're constants and not rational functions of Z like they were in the previous slide. This is Z itself, and so it's some polynomial. So I've just replaced that, and then of course I've replaced S with what it is. So you have to be able to integrate this thing. And this thing is going to break down by its sum, well, plus of course, you've got to be able to integrate this guy too, right? So I'll put that right there. Integral Q1 Z over QD Z of S dz. But we're focusing on the first part. But this one, you can break this down into its sum, right? I mean, you've got a constant over the radical, you've got a linear term over the radical, you've got a squared term over the radical to some arbitrary power over the radical. So clearly, this is going to require that we are able to integrate 1 over radical CZ squared plus BZ plus 1 dz. We need to be able to do that. We need to integrate Z over square root CZ squared plus BZ plus 1. We've got to do that, Z dz. And then we've got to be able to integrate Z to, we'll call it the K, some arbitrary number K, square root CZ squared plus BZ plus A. These should be A's, not 1A. So you may say, well, this is kind of redundant, right? If Z to the K, well, I just set K as 0 and I get this. I set K as 1, I get this. And set K, I get this. But if you're experienced with integration, you kind of know that when you see these arbitrary K's, there's going to be some kind of integration by parts. You're going to express it in terms of the integral with a reduced exponent. And your base cases are probably going to be these. So in anticipation of that, we're going to say, yeah, but I've got to learn how to integrate this. I probably need to learn how to integrate this. And I bet with these two, I can integrate any of these. Now, again, I know that because I know the answer to the puzzle, right? We know how to do these integrals. So I'm clearly working backwards here, but you can understand that is sort of the reasoning. That's why I'm saying that we need to know these three and not just this one. But technically, yeah, we need to know how to integrate this. The point is that for arbitrary K, we're going to get a formula, but that arbitrary K will have the condition that it's bigger than 1, right? So we have to solve these two as special cases. So I'll put a red box around it saying, if we want to be able to claim to integrate all rational functions involving Z and S, then we better be ready to integrate all three of these. Okay, so that's on our to-do list. Now we have to, but that just attacks this term, right? Now we have to look at this term. So let's do that. Now this term is not that bad of a mess once you kind of get what we're doing here. This numerator is a polynomial in Z. So we have these now constant coefficients, right? Earlier this notation was used for rational functions of Z, but now Z is actually our is explicit here. So these go back to being constant coefficients. So here's some polynomial in Z representing Q1. QD, likewise, is some polynomial in Z. Whoops, I forgot there's an S down there, right? This term is this term here. It's Q1, QD with that S, right? So, but the term in the denominator, instead of breaking it up into its polynomial, we're going to assume it's been factored. So whatever polynomial this QD is, it's got roots, real roots R through R sub, I guess that should be R sub H. And the multiplicity of each of those roots is N, right? So root R1 has multiplicity N1, root RH has multiplicity NH. And then the conjugate complex root pairs are expressed as just factorized quadratics that can't be reduced to real products, and they also have a multiplicity. And I didn't write them here, but there's some number of these, say j of them. So there's going to be j terms like this all multiplied out in the denominator. The point is the denominator is fully factored where the real factors are explicit and the complex factors are still bundled in these quadratics. Now, and then of course S is the square root of C z squared plus bz plus a. A looks like a 9 plus a. That's what S is. Now, if we were doing this in complex, in the complex plane, meaning z was to be treated explicitly as a complex variable, you actually wouldn't have these terms. Everything would look like these, and now the roots would be allowed to be complex as well. And these would come in complex conjugate pairs. So, and that's important to understand because when we study elliptic functions, all of the literature of elliptic functions is almost all done in the complex plane. So we'll have to adjust, in which case, by the way, some of the analysis we're about to do gets simplified. It actually makes it a little bit easier. The harder part is you're dealing with complex numbers. But anyway, this term breaks down into this. So now the question is, can we break this down? And of course we can, right? That's what we learned or reminded ourselves about in the last lecture about partial fractions. This expression can be broken down into the partial fraction terms in a very specific partial fraction, a sum of terms that are expressed in a very specific way. The first thing to sort of realize is that this S is a common factor here. This S is a common factor. And so we could write this thing as 1 over S times, and inside here we'll put our partial fraction decomposition. And the partial fraction decomposition will always contain terms that look like some constant, I'll just have to say A1 over Z minus R1, right? And this will come to an exponent. There'll always be an exponent here. I'll say, I guess I'll just call the exponent j. And then you'll have a bunch of terms that look like that, right? So for example, if n1 was 2, you would have a term that was linear and then a term that was square, right? As part of our partial, if n1 is 2, then you're going to end up, the partial fraction contribution of this root is going to have two terms, one that's linear in this z minus r1 and then one that's the square of z minus r1. And likewise, you'll have the same situation over here, except in that case, you'll have something like b1z plus c1, and that will be over d1z squared plus e1z plus f1, and then it'll have some exponent. I'll call that exponent I. Let's see, let's clean up my I there. I. Right, so the partial fraction decomposition is pretty straightforward. And then if you remember this 1 over s, and now from that tells us that in order to integrate this, which would be integrating that, you're going to have to be able to integrate terms that look like this, not forgetting that there's an s there. So what does it actually amount to? It amounts to integrating the integral, let's say, of something that looks like a, some constant a. I won't even, well, I can't, I don't, if without the subscript, you're just going to confuse that a with the a that's buried in the s, right? So what do I do? How about, I'll just call it g, little g, and it'll have to be z minus r1 to the I-th power times the square root of c z squared plus b z plus a. That's the a I was going to worry about. dz. We have to be able to integrate those, and we have to be able to integrate hz plus k plus a little l, and it's got to be d1 z squared plus e1 z plus f1, that raised to the I-th power times the square root of c z squared plus bz plus a dz. So we have to be able to integrate these two things in order to be able to integrate that. And then if we can get these two here, right, and if we can do these three here, then we can integrate any rational function that involves s. All right, so the rest of this lecture is going to be to do some of these integrals. One of them is just too tough to really go through. I'll cite a reference for it, but we'll knock through these integrals pretty quick. But if you're not interested in actually going through the nuts and bolts of these integrations, now's the time to just stop and move on to the next lecture. The basic idea that we have to learn is that the integration of any rational function regarding with this radical in it is doable. And now we're just going to sort of clean up the mess that we've made. But with this, we know that we can convert this into another integral that looks like this. U squared plus or minus capital D squared. And that substitution we did in the last lesson, but basically this quadratic always can be converted into C times U squared plus or minus D squared. So I guess there should be a 1 over what? 1 over square root C, right? And so that conversion can always be made. I think, if I recall right, the substitution is U equals Z plus B over 2C, and D squared ends up equaling the magnitude of 4CA minus B squared, which is sort of the reverse of the discriminant as we normally know it, magnitude over 4C squared. And then the plus or minus is chosen based on the sign of 4CA minus B squared. So that's the plus or the minus is related to that sign. So with this substitution here, you calculate dz from this, you can get a conversion into that form. And once you've got a conversion into that form, you can do two things. You can do the substitution. Let's see, which substitution would you do? One substitution would be the du. Let me get it right. No, you would get u equals d secant theta, right? And then that's if you have if the plus minus is actually a minus, right? If you got the minus case, you would use secant theta. And then the idea here is that you're working the Pythagorean identities of trigonometry, the various Pythagorean identities. And when you're done with all of that, you end up with plus or minus 1 over the square root of c, times this logarithm, right? This logarithm here. The logarithm shows up because it turns out the integral of a secant ends up being a logarithm. That's not one of the ones I had memorized. And then, of course, there's the integration constant down here. Then, you have to substitute. To get all the way back, you have to take these substitutions and go back in there, and ultimately you end up with an answer. The answer I'd like to, this integral, the way I'd like to focus on it is a little different, though. I want to use this hyperbolic function. u is d hyperbolic cos t, du is hyperbolic sinh t. With that, you get a different expression than you would have with the secant. And the substitution is pretty simple when you do this hyperbolic substitution. Starting with this expression, you end up immediately with this expression where you then can pull out this d squared up front, and you end up with basically hyperbolic sine over hyperbolic sine, which is just the integral of this constant times dt. So you get t over d root c plus some constant. And once you have this configuration as your answer, whenever you can get the integrand to zero out, you know that you're going to deal with an inverse function, because now you've got to invert u. You've got to find t as a function of u. So the only way to do that is the inverse hyperbolic cosine. So you're going to end up with the statement as such. You'll get this integral is this factor times the inverse hyperbolic cosine. And what you're essentially doing when you do this, by the fundamental theorem of calculus, you're going to get that the definition of the inverse hyperbolic cosine is actually defined this way. Is actually defined this way. And that's what I kind of want to get at, is that, again, we have a circumstance where we can actually define, what am I trying to do here? Inverse cosine, cosh, of t, inverse cosh of t by the fundamental theorem of calculus, right? So this is the definition you're forced upon. That's forced upon us. So we've essentially discovered the inverse hyperbolic cosine as this integral defines that inverse hyperbolic cosine. And notice the argument of the definition is in one of the limits of integration. And that's by applying the fundamental theorem to this idea, to this guy right up in here. Meaning that the derivative of this must equal this, right? And that's how we're going to define our elliptic functions as well. We're going to be in a similar situation, and we're going to define our elliptic functions in a similar way. So now we turn to this guy, this first power of z in the numerator, and there's a very non-obvious substitution, though, that quickly tears apart this integral. And here it is. We substitute this whole guy here down here. That's u. It's a substitution that you can't imagine would work. It's like the first thing a naive student might try is, oh, maybe if I substitute this away. But in this case, it actually does work for our purposes. So u is that whole quadratic under the radical. And then if you take the derivative of this and you do a little calculation, you get z dz, which is the numerator, is going to equal du over 2c minus b over 2c dz. So it's a little weird because you're substituting for z dz, but you're not substituting it totally into the new differential. You're substituting it into this pair of differentials. So obviously there's a trick ahead. And first let's execute the substitution. Let's see. And that substitution gives you this. It gives you 1 over root 2c times the integral of du over u. This is an elementary integral that we can quickly do. In fact, this will end up being, well, why do I have a square root there? This shouldn't be a square root. This should just be c, right? Yeah. And so this should end up being 1 over 2c times the square root of cz squared plus bz plus a, right? That's this integral. And then this integral is of the exact same form that we just did over here. This is this guy right here. So we've reduced this integral into a constant term minus an integral that we know how to do. So this integral can now be completely solved. Except this here, yeah, this is a factor of 2. So I put the 2 in the wrong place. So it's 1 over c, right? The integral of du over square root of u is like u to the minus 1/2, which is going to be u to the 1/2 divided by 1/2, which was the 2 in the numerator, so that would cancel that 2 in the denominator, and so you end with 1 over c. Whatever, you can look this up, but that's right. So we've reduced this one, so now we'd go on to the next one. Now this guy is a lot of fun if you're into this sort of thing, because we're going to develop a recursive process to solve this integral and turn it into integrals of terms where the numerator's degree is less than z to the k. It's going to be z to the k. We're going to have this in terms of something that looks similar with z to the k minus 1 and z to the k minus 2, two integrals essentially of this form. And when we do that, we can presume that we could repeat that process on these guys until we end up with this guy and this guy at the end, right? So that's the goal for this section. So we're going to start by making some clever observations, and I don't know who first figured this out, but people thought about this. This was advanced mathematics at one time, and all the great minds were thinking of these things, and this is what they came up with. I certainly would not have stumbled upon this if this was on a test. But anyway, look at the derivative with respect to z of this expression, z to the k multiplied by our radical. And I'm going to change our radical. Whenever you see this, it means this. And that derivative is simply k times, using the product rule, is pretty straightforward. We're taking the derivative of this term and multiplying by the derivative of the inside, which is that, and you get z to the k up there. So once we make that simplification, we can keep simplifying things. So our next step is we pull out a z to the k minus 1 divided by 2 times radical box. So to do that, this z to k minus 1 comes out from this first term, but to get this guy, I have to put the box here and then pull out a 1 over radical box here, so that when multiplied, and then the 2 I have to multiply by 2, so that this term and this term will result in a radical box up in the numerator, or left over. And then here, I pull out a z to the k minus 1, so I have to leave a z behind. This guy stays behind. The 2 comes out. Let's see. The 2 comes here, so I have to... so that 1/2 comes out too, and then the radical box comes out. So that leaves us with this expression. So now you can simplify this into this form, where you see what I've done is I've turned it into a regular quadratic, right? Here's the z squared term, here's the z term, and here's the constant term. So 2k times radical box, remember 2k times box, for which there is no radical, it's just going to be 2k times cz squared. So there's 2k cz squared, and then where are you going to get the 2? You got a z here and a z here, so you have 2cz. So there's 2cz. So you see how you can break this down and get this in its little quadratic form. I guess the 2k plus 1bz is this 2k times the bz, so that's the 2kbz, and then where's the 1bz? Oh, here's a b and here's a z, so that gives you the 1bz. And then 2ka is obviously 2k times a over here. And there's no constant term here because everything's multiplied by z. So this is a quadratic that's totally equivalent to that. So now we integrate. So let's see, the integration starts with integrating the left-hand side, but the integral of this derivative just brings back this term, so it's z root box, because remember this is box. And then integrating this term here is, well, I guess now integrating this first term, so this z squared turns the z to the k minus 1 into z to the k plus 1. The 2k plus 2c is a constant, then you get this root box. Let me see, where did my factor of 2 go? You know what, I'm just going to multiply this whole thing by 2, right? I'll just take that 2 and bring it over to that side. Okay, so that's the integral of this term. Now the integral of that times this term is b to the 2k plus 1. Then this z goes to that minus 1 to give you z to the k over root box. And then the last one is just 2ka times this term, so 2ka z to the k minus 1, which is that factor over root box. So now I have this equation, right, which connects the integral of z to the k plus 1, z to the k, and z to the k minus 1. So I'm interested in the integral of z to the k, remember, that was sort of our goal here, right? That's the problem we're solving, is z to the k over root box. So what I'm going to do is I'm going to shift the index k. I'm going to shift the index k, and so I'm going to write k, let's see, what'll shift it correctly, k plus 1 equals n. So I'm going to call k plus 1 equals n. And then I'm going to rewrite this whole expression with this substitution, k plus 1 equals n. Totally semantic maneuver. Well, let me say I'm going to make the substitution, and then when I substitute k plus 1 for n, this will become z to the n. So I'm going to make the substitution, this substitution, and then I'm going to solve for this integral, which will be z to the n. And then, of course, k will be n minus 1, and k minus 1 will be n minus 2. So we'll see we'll have an integral for z to the n in terms of the integral for z to the n minus 1 and z to the n minus 2. And that will be our sort of recursion process. That will be the top level of our recursion process. And here's that final result, I guess the best of my little calculation. Here's our integral, and this is just a calculable term, right? This is a constant term. Well, it's not a constant term, it's a function of z, right? So that's why the integral is this function minus these functions, which are further integrals, defined through further integrals, but you'll see it's the n minus 1 version, the n minus 2 version. And obviously this will work up to when n equals 2, right? You're going to get it in terms of z and z to the first power and z to the 0th power, which we've just previously solved. So that shows that we can now do any form like that. So that means that we can now integrate this guy here and this guy here and this guy here, which I think covered these three. This covered these three. So, and this, remember, we're going back to the idea that we're trying to integrate, whoops, that's these three. We're trying to integrate any rational function like this ultimately, right? So now we've got a good chunk of it, but now we've got to get these two. Now these two are definitely harder to do. I probably will decline to do this one during this lecture, but you can look this one up in Gradstein and Rizdik, page, well, let's see, I shouldn't cite the page because everybody has a different version. Let me write this down. I'm assuming that everybody knows what I mean when I say Gradstein and Rizdik. It's called the book's called The Table of Integral Series and Products. It's a standard reference book you'll find in every single library. I won't cite the page number. It's page 81 in my version of the book, which is, gosh, I don't even know what version this is. This is, wow, I think I'm probably using an old one here. Mine is the 4th edition, so in the 4th edition it's on page 81, but the section is 2.252, and I'm pretty sure that doesn't change between versions. But that will, in the last part of that section, show you the amazingly bizarre Rococo level substitution required to solve this. And it's not very insightful exercise. It's got to be a hell of a lot of algebra, and I confess I haven't bothered to do it. But it will get you to reduce this integral here into forms that are increasingly solvable. Now, this guy here, however, isn't quite as bad, and maybe we can work on that one. Yeah, just checking the same section of Gradstein and Rizdik, it actually describes the substitution for this one, which is much more manageable. This one seems to be a real bear, but this one I think we can actually tackle. And this is the basic substitution we're going to do. We're going to, t is 1 over z plus p, and the subsequent solution of z and dz. So if we make that substitution back into here, what do we get? Let's see, this is my first attempt at the substitution. It's pretty straightforward. You see what's going to happen. This z plus p. By the way, this form is the form of the integral we're seeking in Gradstein and Ristic. I guess the one where we ultimately started with was z minus the root, but Gradstein and Ristic uses a plus sign there, so I'm duplicating their format. So if you check the references, you can get it. The nature of the integral is the same, but you'll see you get the minus p from here, and then the plus p. So those two are going to cancel out, right? And then you're going to get a 1 over t to the k after that happens, and that's going to go upstairs, but then you're going to get this t squared downstairs. So you'll get the minus sign out front, right? The t squared will come down, and then you'll get t to the k up here. So then what we'll have to do is we'll have to expand this. And you can kind of see what's going to happen. When you expand this, you're going to get a 1 over t squared term, a 1 over t term, and a constant term. Here you'll get a 1 over t term and a constant term, and then this will be a constant term. The 1 over t squared term, when you pull this guy in, then this guy will go under the radical, and you'll get a t to the 4th power. It'll combine with the 1 over t squared to give you a t squared term, and then it'll combine with the 1 over t term. Well, let's just do it. So this is the expansion. You can see, so you're going to get a 1 over t squared times c, that's this one, and then you'll get 2p 1 over t with a minus sign like that, and then the p squared like that. This will be b over t minus bp plus a. So now we will, I guess we don't take both t, we don't put a t to the 4th in there, because then you'll end up with a t squared here, a t cubed, and then a t to the 4th. I want this to be quadratic, so I'm only going to take one t in. I'm going to take in just one t. So what will happen is this will become, leave a t outside, and I'll bring a t squared inside. One of the t's coming under the radical will be a t squared. So that's going to cancel with this to give a 1. It's going to put a t there in the numerator. It'll put a t squared there. It'll cancel with that to put a t there. And then it'll be a t squared here and a t squared there. So let's simplify that. And this is what I get. I get that t that's left behind comes up here and gives you that. And then you have, if you collect all the t squared terms, you get a p squared, a minus bp, an a. You collect all the t terms, you get a minus 2p, which is that, and a bt, which is that. And then the only constant term that sticks out is this guy right here, which is just c. Okay, so that, I think, is, well, I guess that's the answer, right? So the reason this is the answer is because this, let me change color. This part here, I could call that gamma. Here, I could call that beta. And then this c, I guess I could change its name to alpha. And you end up with the integral of t to the k minus 1 over the square root of gamma t squared plus beta t plus alpha, which is essentially the problem we solved right here, right? That's what this problem is, just with a k instead of a k minus 1. So we've now reduced that integral to something we've already solved. And again, this integral, which we've reduced, we've essentially, this is a very important point. This integral that we've learned how to solve, ultimately, is we've got this recursive relationship, but that recursive relationship bottoms out here and here. So those are the two core integrals we need to know, right? So I can always, so notice how I'm going to say this. I can always express the integral, this integral, in terms of this integral and this integral. So there's really two fundamental integrals those two that I just showed, because I've reduced everything to a problem involving those two integrals. Now I've taken this problem and I've reduced it to this, but that again reduces to those other two integrals that I've already need to know, those two fundamental integrals. And ultimately, when I talk about elliptic integrals, that's what those elliptic integrals are. These are equivalent to the elliptic integrals in the sense that there's a certain class of function who can be reduced to these basic three elliptic integrals. But these guys are not that, but it's similar in process, right? We need to know how to do this, and we need to know how to do this, and then everything else can be reduced to those forms. I'm kind of, when I go through this integral, I'm actually talking about the mechanics that ultimately bottom out with those other two integrals I just showed you. So then I'm not going to go through the substitution for which one? That other one. Where was it? This guy. I'm not going to go through that substitution. It's actually horrendous. I'll just write it down so you can see it, how horrendous it is. Actually, I started to write it down, and it's so horrendous that I don't even want to write it down. So, but have no fear, this integral also ultimately reduces to the same two integrals, which are going back to it, which are this one here and this one here. So even this first one, that guy reduces to those two that I made in green, and then the other two that we talked about, these two, are also reduced to those two in green. Okay, so that solves the problem of how to integrate any rational function that looks like this. Our next step is talking about the actual elliptic integrals, which is a very, very, very similar process. Okay, thanks, and I'll see you next time.